The review of Arctic dynamics has shown up many of the mechanisms that are determining change in the Arctic region, which is happening at an extraordinary pace. Now I want to move on and look at some of the consequences and implications of Arctic dynamics. First of all, we're going to look at the runaway behaviour that is actually happening to the Arctic system. As we reviewed those 3 or 4 parameters, we saw the temperature change going almost exponential. We saw the rate of change of ice area accelerating. We saw the change in ice mass or thickness also accelerating and moving towards zero over the next 2 or 3 years. And taken all together, we have the unmistakable footprint of a system in what we call self-amplification or runaway behaviour. It is already feeding on itself, the albedo feedback, the water vapour feedback, the ice albedo feedback, and other factors all combine to amplify the effects of the carbon dioxide trigger to the dynamics in the Arctic. And in a sense, the human trigger is now almost irrelevant. The feedbacks have taken over. So that's what we mean by runaway in the Arctic system. The second consequence is the increasing ice-free window. You will remember that we saw that by the end of September, which is the minimum period of Arctic ice, we would expect there to be virtually no ice at all floating in the Arctic Ocean by certainly 2014, 2015. And what we're talking about there is just a few days of ice-free condition before it begins to set back in again. Now, during that period, all the sun's energy that had been going into changing solid into liquid, melting ice into seawater, and remember the rate of that was running at about 1,300 cubic kilometres of extra ice melting per year, that energy is available to heat the water instead of melting the ice during that little window. And all the solar energy that was being reflected from the ice is also available to heat the water. So during the ice-free little window, warmer water is being set in place, ready for the next autumn. That means that when it does start to freeze again, it freezes later, the ice that is formed is thinner, and then the next year, when the melt sets in again, there's thinner ice, and there's less of it, and it melts sooner. The result is that once that ice-free window has formed, it expands year on year on year. And because of that, all the energy during the ice-free window goes into temperature change, and we see a discontinuity from a smooth upward curve in the temperature to a sharper upward curve in the temperature at that point. So that moves us very naturally into consequence 3, that consequence of the acceleration of temperature in the Arctic region is very important indeed. As the temperature starts to increase more quickly, then other feedbacks are also brought into play, and more powerfully than they had been previously. So, as an example, as the temperature change increases, so the rate of water vapour feedback also increases. The effects on the amount of solar energy that is available to the Arctic region is also a feedback, because with later formation of the ice, there's less solar reflection in the late autumn, and with earlier ice freeness in the late summer, there's less reflection in September, August, maybe even July. And so the whole process is accelerated as the ice-free window expands. So those two consequences are deeply linked. The widening window of ice-free behaviour and the accelerating temperature. Let's move on now to the fourth consequence, and that is the impact on the tundra. Those land masses that border onto the Arctic Ocean now have a warmer, open sea coast, and the warmer air and the warmer temperatures are being fed back over the land mass. And of course what that does is increase the rate of melting of the tundra permafrost. And we get this depth of permafrost melt, or which we call the karst, increases year on year. That also has consequences. For instance, there's a lot of biological material in the deep freeze of the tundra, and as that thaws out, it begins to decay. The microbes have a field day, and out comes more carbon dioxide and more methane from the rotting vegetation. That adds to the feedback loops that concern the greenhouse gases in the Arctic. As the karst goes deeper and as the surface warms more, there are two other issues at stake here. One is, of course, it takes longer to freeze in the autumn. The snow is less extensive and lasts for a shorter period, so there's less solar reflection from that. And also, during the summer period itself, the warmer water from the tundra that is running north through the rivers and into the shallow seas across the continental shelf is increasingly hot. So we have warmer water coming into the shallow seas of the Arctic. All sorts of feedbacks in this very complex system. The fifth implication of the Arctic dynamics concerns the feedback of the methane release. It is probably one of the most important issues that we have to examine. With ice-free conditions and warmer waters, and therefore the surface of the ocean available for wave energy and tidal energy and storm energy, which when covered with ice did not affect it. So surface water is being driven down and mixed with the deeper water, particularly over the shallow continental shelf areas. And as the water temperature at the bottom of those shallow seas increases, it begins to release methane that has been stored in what we call clathrates. That's a kind of combination of methane and ice crystals. They're kept there under water pressure and temperature conditions. As the temperature rises, the methane begins to be released. Some of it gets absorbed in the column of water, some of it begins to bubble to the surface. And the faster the temperature increases, the faster the release of the methane, and the more reaches the surface. Oh, and underneath the ocean sediment there is a fossil area of ancient ice left over from previous ice ages. What we're seeing now is that this fossil ice is beginning to rot and melt, and methane from beneath it is beginning to bubble up through it. So methane is being released into the atmosphere, not only from the ocean floor, but also, as I said, from the melting of the tundra. And the more methane there is in the atmosphere, as this next slide shows, the greater the greenhouse effect. And methane is a very powerful greenhouse gas. And as that concentration goes up, so the rate of heating in the Arctic goes up. And the faster methane is released, the longer it stays in the atmosphere before it breaks down into carbon dioxide and water. So there's a second feedback that makes the methane feedback more powerful the faster it goes. And the faster it goes, the more powerful it gets, and so on. So we have another runaway feedback process able to be triggered by Arctic dynamics. It's been called a methane bomb, but I think that's a misnomer. It takes a lot of heat and energy to melt the clathrate deposits on the seabed. So the rate of release is determined by the rate of mix down of warmer water to the seabed. That is a fairly slow process. There are some possible releases of large amounts of methane from the seabed, but overall the methane release is a fairly slow cascade feedback that could take decades to centuries. It does, however, have enormous consequences for the rest of the world, as well as the Arctic area. Let's move on. The sixth consequence concerns what's happening to the Greenland Ice-Cap. Now, it sits there as a 1.5 mile thick layer of ice across a large piece of landmass. And you'd say this is immovable. However, as we move to acceleratingly increasing temperature change, as the waters all around Greenland are no longer covered with floating ice, and as the temperature of those waters around begins to increase, so of course the air over Greenland is hotter, the waters around it are hotter, the ice surface begins to melt right across the dome of the ice cap, and we saw a 97% area of melt this last summer, which is unprecedented. We can expect that to increase, and the period during which it's happening will start to widen. Now, the pace of change of the Greenland ice cap historically has tended to be quite slow. We do have evidence, however, of episodes of quite rapid melt, say on a decadal basis. But with the rate of change in the Arctic, nobody knows now how fast the Greenland ice cap will respond. We do know that the rate of melt is accelerating, and therefore there are several consequences here. As the surface melts, so it becomes lower. The lower it gets, the hotter it gets, and the faster it melts. The faster it melts, the more water is being channeled down through cracks to the base of the ice. That frees it up and starts to make it move more. When there is no ice around the edge of it, then glaciers moving into the ocean are free to discharge and to carve into icebergs more quickly. So the collapse of the ice sheet could become exponential and could happen quite quickly. And as that happens, then a lot of fresh water from the melting ice is discharged into the North Atlantic, and that can have implications for the drivers of what we call the Gulf Stream, the thermohaline circulation. And if that slows down, and we would expect it to under these conditions, then the heat that currently comes through ocean currents to the western coasts of Europe begins to decline. And in a strange anomaly, the rate of change, the rate of heating in the western seaboard of Europe will become slower as global heating takes over and as Arctic temperatures rise. So, the consequences for the Greenland ice cap are massive. And as it melts, it adds fresh water to the global ocean and starts to raise the sea level. And if it goes quickly, then we can expect 2, 3, 5, 7 meters of sea level change right across the world to happen on a decadal basis, i.e. within 10 to 20 years. That would be catastrophic for civilization, many of whose urban centres would be below sea level in the new situation. The temperature in the Arctic goes up and therefore decreases the gap between the cold Arctic, which is getting warmer, and the warmer subtropical areas lower down the latitudes. Now, The difference between Arctic temperature and subtropical temperature is what drives the energy of what we call the jet stream, that is contained as a vortex and goes around the pole. And as the difference between Arctic cold and subtropical warm decreases, the energy of the jet stream begins to relax. And instead of storming around as a vortex, it becomes more meandery, like a river that has met the floodplain, and it starts to move in loops. And then the less the difference becomes, the slower those loops move around the planet. Whether you look at some of the mathematical treatment of this coming out of Potsdam at the moment, or the beautiful analysis of the actual information and data coming out from the work of Jennifer Francis, the same understanding is there. What are the implications of that? Well, first, the jet stream relaxes and moves south. So some of the colder area hits into the northern areas of the big continental landmasses. Oh, and the meanders mean that in certain areas, cold air from the Arctic is being drawn southwards. And because the meanders are slowing down or even getting stuck, we get these long periods of extreme cold air pouring Arctic conditions down into the continental landmasses. We've seen that happening in the last 2 or 3 winters. And the other thing is this: in other areas where the loop is the other way around, there's warm air being drawn up into the Arctic from nearer to the tropics. So we've got a heat exchanger going on. The fridge door's been left open, so all the cold air is leaking out at the bottom, and the warm air is being sucked in at the top, and that increases the rate of temperature change in the Arctic, which decreases the gap between the Arctic temperature and the tropical temperature, which increases the effect on the jet stream, makes it meander more lazily, and increases some of these blocking patterns of extreme drought, extreme rain, extreme cold, extreme heat, and the extreme unpredictability. And that's where the nub comes. With the unpredictability, and look at the areas we're talking about, the breadbaskets of the Northern American plains, the corn-producing, the wheat-producing areas in Europe, in Russia, in Ukraine, and across into China, and the northern rice-producing areas. So we've seen already major loss of food production capacity in the Northern Hemisphere as a result of what has already happened. And over the next few years, that will accelerate significantly. There are economic issues, there are humanitarian issues, there are political issues that stem from that instability. We're already seeing hedge funds and investment funds buying up future food on the understanding of shortages caused by this phenomenon. And that means it's going to be very difficult for the poorer countries of the world to buy food on the open market to enable their populations to survive. It's even more difficult for the aid agencies to buy up surplus food on the market, which is now much more expensive, in conditions of humanitarian disaster. And because this has economic spin-off, there is destabilization in the wake of food shortage and political destabilization. So we have some really important issues to deal with as the implications of the phenomenon that we are now understanding in terms of Arctic dynamics. And that brings me to my final section in consequences and implications of Arctic dynamics. What are the implications of all this for global dynamic behaviour, both in climate and indeed for humanity as a civilization and the biosphere of which we are a part? Well, obviously, the Arctic is connected to the rest of the world. It is part of the world, and what happens in the Arctic inevitably has implications and consequences and spin-off for the rest of the planet. Part of the planet is in Runaway. Most of the rest of it is in stasis. In other words, temperatures are held stable at the moment. Socially, we know we will be beginning to remove some of the aerosols, the particulates in the atmosphere that at the moment are reflecting much of the solar energy back into space. We also know that much energy is being taken up by heating of the deeper ocean at the moment. And as the effects of carbon dioxide and the other greenhouse gases in the global behaviour as a whole begin to come back on stream, so global temperatures will begin to respond much as Arctic temperatures did. CO2 begins to increase temperature. Increased temperature drives water vapour feedback. Water vapour feedback accelerates heating. And then we begin to get hotter conditions for some of the tropical forests. We get burn and dieback and increased release of carbon dioxide from the biomass of the planet. It's a different set of feedbacks from that operating in the high Arctic, but it is nonetheless potent. And as in the Arctic, so tomorrow in the world as a whole. And if the implications of jet stream behaviour and food production and Arctic dynamics spin off into our survival as a species, into our economics, into our food production, into the abandonment of the poor and the inability to sustain a population of 8, 9, 10 billion people. So also the increasing acceleration of global behaviour, which will inevitably follow unless we are able to intervene, to slow it down, bring it to a halt and reverse it, then without that intervention, global dynamics hold a dark future for humanity, a dark future for the biosphere of which we are a part. It is time to take action not only for the Arctic, but for the global crisis in which we are all placed. Thank you very much.